Hello, this video is about the Nobel Prize in Chemistry 1914, awarded to Theodore William Richards for his accurate determinations of the atomic weight and the large number of chemical elements. You see the book he wrote about the subject. And you see some of his results. And here we see the name of the lecture, Atomic Weights, summarized by me. And here we go. The great Berzelius was one of the great leaders of chemistry. He made accurate revisions of Dalton's atomic weights. I am a modest follower of Berzelius and try to advance on his work. Ungrateful would he be who failed to remember his step to his predecessors, not only Berzelius, but also de Marignac, Stas, and others who have done so much for the study of atomic weight. The study of matter and energy can contribute to a better understanding of life. Here we study the most important attributes of all chemical elements. All matter is composed of negative electrons and positive nuclei. The old elements are still worthy of recognition, the ordinary are still permanent as they were before the discovery of radioactive elements which fall apart. For practical purpose, the elements, even in the end, may all decompose, are the obvious basis for our reasoning. The only radioactive elements we know have an atomic weight of 210 or more. The essential elements for all life have an atomic weight of 56 or less. The data I first decided to study was atomic weights, which are definite and unchanging. They do not only represent the relative weight in which substances combine with each other, the relative in which the masses combine, they give us a picture of the average relative weights of the atoms because they represent gravitation and mass. The law of combining proportions is one of the few very precise laws of the universe, complicated to an extraordinarily small degree by superimposed irregularities. We cannot understand the atoms if we do not understand the significance of weights. The beginning of the universe is engraved in the atomic weights. In that sense, the periodic table is the Rosetta Stone which enables us to understand them. Any new insight in the nature of atomic weight adds greatly to our general insight about matter. Besides atomic weight, other properties are worth investigations, like compressibility, but these are not the subject of this lecture. Today's lecture is about atomic weights. Experiment of great refinement is necessary in order to determine economic weights. No atomic weight of one element can be used to calculate that of another. The first step is to have the elements isolated in a pure state. This is not easy. All impurities have to be excluded, and not all elements can be isolated, thus compounds have to be used. The choice of a usable compound is extremely important. The second task is the preparation of the substances in the state of greatest possible purity. There are many reasons why impurities may be in the substance. Constant and rigorous testing is needed. Also, after the preparation finish, contamination danger is everywhere, always there. The substance must also be collected to the last trace and brought onto the balance pan, if not the qualitative experiment fails. This can only be done by ceaseless attention to the rules of the procedure, controlling and checking, etc. Special experiments are conducted to prove that all has gone well during the measuring experiments. First, it must be checked that nothing is lost, and second, that no combination with a foreign substance has occurred. Before anything is published, it must be proven that nothing has gone wrong, instead of leaving this to subsequent investigators. The first study I did on atomic weight was a comparison of the atomic weights of oxygen and hydrogen assisting Parson Cook. It showed that the ratio is considerably less than 16:1. After 2 years of work, we came to the conclusion that the atomic weight of oxygen is not far from 1.008 if oxygen is taken as 16. Morley and Rayleigh measured the now accepted value as almost the same. The next study on copper, carefully purified, coming from many sources. The outcome corrected the accepted atomic weight of copper by nearly 0.5%. It then became clear that the atomic weight of barium was also not correctly determined. Later this was also done for other metals of the alkaline earth. That's a group in the periodic table. In 1894, while working on strontium, an apparatus was devised for enclosing, weighing hygroscopic substances out of contact with air. This was devised for cases demanding ignition. When researching magnesium in 1896, this all with the help from a distance, of course. The next problem was to determine whether or not cobalt and nickel have the same atomic weight. The antithesis of copper has it 2 atomic weights. The result was the atomic weight of cobalt is higher than that of nickel. It was expected to be the other way around. The atomic number of cobalt is lower than that of nickel. The periodic system thus represents only in a crude fashion relationships that are really complex and subtle. This is especially true for elements with an atomic weight over that of potassium. Next, I turn to the relation between atomic weights and Faraday's electrochemical equivalence. I followed Lord Rayleigh's work, he should be an Y, who found that a fairly close agreement exists between these quantities, but with a full measure of exactness than Rayleigh's. During these experiments, several early mistakes with the cyclometers for determining weight through measuring electric current were corrected. And I have skipped the details from that. So if you want to read it, go to the original text. You find the link in the description of the video. It was found that earlier the found value for weight was too low for copper and too high for silver. It was found that the atomic weight of silver is half of that of copper and that Faraday's law held true. It was then investigated if change of temperature and solvent had any effect. That did not. Then uranium, already considered of great interest before the discovery of radioactivity. It was a high atomic weight. It was studied for 4 years, starting in 1896. In the end, it was found out, despite difficulties, that its atomic value is about 238.5 instead of the old value of 240. Hönigschmidt came to a value of 238.2 a little later. Passing over no less interesting strontium, zinc, magnesium, iron, and cesium, which contain no new essential lessons. Coming now to the crucial experiment determining the atomic weight of sodium and chlorine started in 1903. Stas studied these with great care, but there were some errors made. Sodium chloride has been prepared in a state of very great purity to find the transition temperature of its hydrated crystals. I found more bromine in it than corresponded to atomic weight determined by Stas. A high value was for the atomic weight was too high. His experiment with common salt had to be repeated. This was not okay. Still, he found the atomic weight of both sodium too large and chlorine too small to be in error due to an impurity in the silver used by Stas. Another fault was that Stas used large quantities of material that could not be properly purified. This all had repercussions for the numbers of other alkali metals, of sulfur and nitrogen. New values had to be determined. Next contribution, compare lithium and silver directly to oxygen. Important because many atomic weights are related to silver and all are to oxygen. Silver has a smaller atomic weight than Stas determined. Lithium's atomic weight was off by 1%, his greatest error. Years ago, Baxter and I worked on the atomic weight of terrestrial iron and found the value had been too high. Might iron from meteorites have another value? Baxter found that they had the same value. It added to the realization of the unity of the universe. Investigation on calcium, carbon, and sulfur varied the work of others. If lead is, as Boltwood suggested, the solid end product of radioactive disintegration, the lead found in radium minerals is of interest. Its atomic weight is the same as that of ordinary lead. Vagans, Ramsey, Boltwood, Gladich, Miner, and others sent me specimens of radioactive lead. I, an assistant, found that its atomic weight is 206.08, ordinary lead 207.2. This is confirmed by M. Curie and Hönigschmidt. No other difference in their properties were found. This is of great theoretical interest. It is not shown if there are other so-called isotopic forms of this kind. For theoretical purposes, this must be investigated. Who knows what modification the periodic system may suffer. Some theoreticians think that the old constants of nature are now less significant. Atoms may be transitory, a substance may have a different atomic weights according to its life theory. Thus, the atomic weights have gained a new significance since it may give clues to the origin and history of the element in question. If the supposed constants are not constants but variable with small limits, this is important for science. Circumstances accompanying the variations must be determined in order to detect a reason for their existence. The subject of atomic weights is thus not completed and closed. Let us hope that finer means of research and deeper chemical knowledge make possible new improvements. Here you see the link to the original text on the official Nobel Prize site. This is only a summary made by me. Here you see some more of illustrations from the book by Williams. Lots of tables with results. Okay, this was it for now. Next week we will go into the year 1915. For now, thank you for watching and maybe until another time.